Without further ado, hi everyone. I'm Jared Longfox. I'm one of your hosts of the AIAA Space Resources Technical Committee's Space Resources webinar series. Excuse me. Today we have Dr. Paul Van Susante from Michigan Technological University here with us to talk about the work that they do in lunar surface ISRU and construction technology. And since the show isn't about me, Paul, I'll kick it over to you. And people, feel free to kick in questions in the Q&A, and we'll get to them at the end. And
All
Paul,
right.
it's all yours.
Awesome. Thanks, Jared. Appreciate the introduction and the invitation to host this webinar here. So, as Jared said, my name is Paul Van Susante. I'm an assistant professor in mechanical engineering at Michigan Technological University. And today I'll talk about lunar surface in situ resource utilization and construction technology as we have been working on it here in the Planetary Surface Technology Development Lab at Michigan Tech. Of course, just a little bit of background information. Right now, NASA is hard at work to get the Apollo, sequel, the Artemis missions to the lunar surface. And the goal of those missions, of that program really, is to develop a sustainable lunar economy, do things on the lunar surface on a permanent basis, and there's lots of technology needed to do all that. So the sustainable part of that is not exactly the same word sustainable that we use here on Earth, in the sense that it's like green. The idea of sustainable space exploration is that it's sort of self-sufficient in a way. And you often see these kinds of images like you see here on the picture, that are large facilities. You can see factories, maintenance taking place. Of course, there's always the magic glass dome over things, a big linear rail and big solar plants and things like that. And maybe in the future, even things like big solar power satellite installations or O'Neill cylinders like that shown on the bottom right. And so these are amazing future visions, and I'm all on board with all these visions. But the key is you need a lot of things to make that happen. All right. So of course, first one is power. Without power, you can't do anything. Right. And then we can, of course, bring everything from Earth, but it's in the end going to be necessary to use the local materials. And so to do that, we need to mine things, we need to extract things from it, process it, we need to manufacture components, and then of course, if we have permanent human presence, it would be great if we can grow our own food in those places as well. And so lots of mass is needed to do all these activities that people envision. And so using the local materials is what we then call in situ resource utilization, or ISRU. And of course, the activities that we're talking about happening on the moon, but the first business is, of course, to get to the moon. And there are lots of activities in that area taking place, lots of rockets being developed, lots of companies getting involved at the Artemis Accords and things like that. And so the transportation side of things is a very active field, and lots of interesting things happen there. And I haven't personally seen Starship launch, but I always like to compare these massive rockets to the height of the tallest building in my area, which is the building I actually work in, and that's this red line. And so you can see these rockets are, almost 3 times as tall as the tallest building in the area here. And so these are massive machines, large cargo capacity, very different in many ways than the small things that we used to be able to launch to different places. And so this is going to change the game in many ways. Now, the sustainable part and also the economic part of that is always predicated on whether or not there is value to be had in those places. And value can be defined in several different ways, but the value of in situ resource utilization, I think, is often best expressed in sort of three different components. One being independence, right? So think of it as a supply chain, and the supply chain now is shorter because you can make stuff locally. And in turn, that also means there's risk reduction because the supply chain is shorter. So if, for example, there's a leak in some sort of oxygen tank, and you'd have to wait 9 months for replenishment, that could be problematic. But if you can just make some more, that greatly is risk reduction for the mission and the heat people and all that sort of stuff. So I think risk reduction to me is a huge one as well. And then in the long term, also improve life on Earth by moving a bunch of industry off the planet in the end. But I think from a sustainability standpoint for the space program, in a way, I always like to think of it as in money equals number of rockets launched, in a way, right? And so if I have to launch fewer rockets, that means it costs less and I can do more for that program. And so an example is here going to Mars, right? I start with 226 kilograms on Earth, and I launch it to Mars, and I end up at 1 kilogram on Mars. Right, so let's say that's one rocket, and I have one payload on Mars. That's great. But let's say I want to come back. Right now, instead of having 1 kilogram only useful stuff on Mars, now I have to also bring the return vehicle, the propellant, the other things for the return voyage as well. And if that's your goal, then instead of starting with 226 kilograms, you need to start with 7,500 and some kilograms, right? If you think of that in number of rockets, right? So instead of one rocket, you need 51 rockets to launch to Mars, basically. And so that's where the sustainability part comes in, where if I can make on Mars 51 kilograms of propellant, right, then I can send that 1 kilogram back to Earth with material made on Mars. So that saves me a lot of rocket launches from Earth to then send it back to Earth from Mars. And so that to me is really the value of ISRU, is where you greatly reduce the number of rockets you have to launch from Earth to go to other places in the solar system. All right. Then we're talking about rocket propellant. Because rocket propellant is the largest mass of the rockets. That's the delta V needed to get to other places in the solar system. And that is the biggest mass of any rocket, basically. And so where can you find that water? Well, on the moon, there are some cool places, literally very cool in the sense that they are in the permanently shaded regions on both the north and south pole of the moon. And in those places, the sun never shines. And so those places have accumulated water ice over the millennia and billions of years. And that ice is in those permanently shaded craters. There, we could potentially extract it, electrolyze it, and then we have rocket propellant. So that is one of those near-term sources that we could use to reduce the supply chain from Earth. Now, what value does that have then? And this is a plot from a study done called the Commercial Lunar Propellant Architecture Study, done by ULA and among others, Colorado School of Mines. And they studied, for example, the value of a kilogram of water from Earth in different places. And so if you have a value of water on Earth, right, it's very little. But depending on where you have to bring it, right, it costs a lot to bring it there. And so the value of 1 kilogram of water goes up. And so, for example, the moon, if I bring it from Earth, right, it would cost $35,000 a kilogram in this study. But if it can make it locally, right, example, this study says that they can make water for $500 per kilogram. If you look at that difference here, that is a huge value proposition for a company, because if I can make it for $500 and the value to bring it from Earth is $35,000, let's say I sell it for $20,000. Now I still give NASA, let's say, a discount of $15,000 a kilogram and still make, $19,000 in profit, so to speak. So this is why companies are very interested, and this is what the value of propellant is in many ways. Now, of course, the value changes depending on the location, because the cost from Earth is also different, and thus you need to take that into account if you want to sell it in other places. But this is a huge thing, because if we can make propellant on the moon and then either bring it to other places and refuel, that allows us now to not be limited to the supply chain from Earth and getting out of that huge gravity well. And so there's some very interesting things that allows. In a way, I like to think of it as it opens up the rest of the solar system. It really breaks down the limitations of the mass that we can send to other places. Now, when you look at this at scale, in the future, right? So what does the growth need? We launch 1 rocket a year, 100 rockets a year. And so NASA and others have sort of studied these things. And so when you look at sort of the future, we're talking about, for example, here, hundreds of tons, thousands of tons a year. Distance traveled, thousands of kilometers per year for the vehicles that need to do the excavation, et cetera, et cetera. So we're talking very large scale. And the challenge with that scale is that it's very different from what we're used to doing in space. For example, if you look at the space rovers that have gone to other planets and driven around on those other planetary bodies, you can see on the right plot here that, for example, the Opportunity rover in 14 years drove about 45 to 50 kilometers, and so that's a nice distance, but it's not anywhere close to thousands of kilometers. And so when we did some analysis on Mars and how we got water from rock, depending on what kind of material you were excavating, you may have to drive thousands of kilometers in this case 1.5 years. And so if you compare that 50 kilometers, let's say, in 10 years to, let's say, 5,000 in 1.5 years, now we're talking orders of magnitude difference in how much performance the vehicles need to have. Not to mention, these vehicles are literally digging in the dirt all the time, versus these science rovers that drive around very quietly, carefully, and touch maybe something here or there. Right? They're very different kind of vehicles, and those are the kind of vehicles, those excavators that drive very long distances, that we're going to need to make this kind of future possible on the moon. And so this is where we get into what we do in my lab, because my lab was founded in 2019. And the goal here is to prototype, build, test, and quickly increase the technology readiness level of technology being developed to enable lunar and Mars missions, and then sustainable space exploration, as I just talked about it, and partner with whoever is interested in making that possible, basically. And hopefully, by doing so, also, we would love to have our own Mission Tech payload on a future mission sometime. And so one of the things that should be clear from this undertaking is that there are many different aspects that need to be developed. And we, in my lab, we can't do all of those things, obviously. So we focus on some subtopics. One, for example, we focus on finding water ice, providing power and communications, extracting and processing the ice. We're doing in situ research utilization and construction, right? So picking up the material and doing stuff with it. And then very important to test these technologies. And there's a variety of different things you need to be able to do that, things like mobility, field testing, lab testing equipment, relevant environment testing, and then, of course, to simulate the moon, you also need the lunar environment and lunar simulant as well. And so here's a little bit of that focus, a little bit split up, if you will. And so, we have robotics and mobility that are sort of a means to an end to be able to do these kinds of things. Then, of course, everything needs control, data acquisition, measurement, to control the vehicles, but also to measure relevant things that you're interested in. And then, we don't just build one, we need to do system analysis and optimize the system depending on the architecture or what kind of mission that it goes on. Right, and so in my lab, we focus very much on TRL 1 to TRL 6, so all the way from the idea to test it in a relevant environment, a space environment, before you would send it into space. Right, and we do a variety of things, particularly in situ measurement of volatiles and geotechnical properties, very important as initial missions to map where we could do excavation of ice, where is the ice, how much is there, how deep is it buried, and how hard is it to get out. And then if you know that information, you can then design better excavators and material handling systems. You got to do construction and compaction if you're going to build road and landing pads for that permanent presence, the infrastructure that you need to do these things. But like I said, everything needs power. And so we've also worked on power deployment, power storage systems, power transfer systems. You can see some vehicles here that we've built. Um, and then, because we have to operate on the lunar surface for many years, move thousands of metric tons of material, wear and durability of the system is going to be really important, because maintenance, the capability, and the access to maintenance is going to be very, very limited. And so we've done testing with materials under lunar conditions, cryogenics with dust and everything like that, to see how long they hold out, or how much wear to expect on a given amount of time. And we do that testing in the lab in the relevant environments, but we also do that in the field. And so there's a variety of different things that we've been working on. And so these pictures you see are all from our tests here. All right, so of course, we need funding to do a lot of this work to make that possible. And so fortunately, NASA has had a lot of funding opportunities. And so this is a little bit of an old graph, fiscal year 2021. But it shows the kind of programs that NASA has, right? So there's commercial lunar payload services, the tipping points, the SBIR program, space technology research grants, et cetera, et cetera. And so fortunately, we've been able to procure these green arrows, a lot of contracts in a variety of different programs. So we have funding from many different sources. And of course, we partner with a lot of companies and other universities along the way. And so in total, we've been able to get about $5 million in funding in the past 4.5 million years to do a lot of different projects. Now, some accomplishments to highlight. Some things I'm pretty proud of. So we won the NASA Big IG Challenge in 2020, or I guess technically it was 2021, with our tethered permanent region, shaded region explorer, which is the T-Rex rover you see down here, which is for power deployment into a PSR, which then led to us being able to participate in the What's on the Moon challenge that NASA had started. And so we are now 3 rounds in, and we're in the final round of What's on the Moon. And likewise for the NASA Break the Ice Challenge, the Centennial Challenge there, we also are now in the final round of that competition. Both will happen this summer. And so this has given about $1 million in prize money and winnings to be able to further develop these technologies, both for power, storage, and transfer, as well as excavating cemented icy regolith. And I'll talk more about those in a little bit. So my lab consists of many different people working in it. And so I'm talking to you, but the accomplishments I'm talking about are done by a lot of students. I have 35 funded undergrad and grad students. We have sometimes students who work for credit as well. I have 2 research engineers working in my lab, and then we have very interdisciplinary approach to things, computer science, electrical engineering, geological mining engineering, civil engineering, et cetera, et cetera. And so basically the contracts and the work we do in the lab is split in 3 main categories. One is the main research grants. These come directly from NASA, and where we are the main research person, doing the research, building the hardware, and then, of course, publishing the results, etc. But we also have test contracts from, let's say, other companies, other universities who want to come and use our facilities that are somewhat unique. And we do that as part of the SBIR program or any other kind of program where we partner with other companies and universities, as well as NASA, to perform testing of various equipment in lunar conditions. And then the third category is student driven. And so we have an enterprise that does lunar related projects. And then we have our competition projects as well. So that's kind of a quick organization diagram of my lab. As you can see, there are lots of people involved, lots of different locations as well. So it's fairly complex to manage it all. All right, so let's talk a little bit about the research facilities in which we do these tests. So one of the big pieces of equipment is a big dusty thermal vacuum chamber, just 2 by 1.5 by 1.5 meters outer dimensions here. And that allows us to mimic the lunar environment. I'll go into detail a little bit more later. But we also have big 40-foot containers where we can prepare the regolith before it goes into the vacuum chamber. And before we put it in the big vacuum chamber, though, we usually do tests in our regular test bed, which is just a sandbox in a way with lunar simulant, before we put it in the vacuum conditions, just to make sure things work under normal conditions, so to speak. Then for field testing, we have a 900 acres proving ground available to us, where you can see here, right, it's right next to the airport, and there are many different drive loops and terrains that can be created specifically for testing lots of vehicles. We have about 25 metric tons of lunar simulant available, so we've also made some sandboxes and trenches where we can then do specific testing that we want there as well. If that is not big enough, we can go out to what we call the stamp sands, which is 1,400 acres of crushed basalt that's left over from the mining days in the area here. And we can do summer and winter testing. And as you can see here, it's very lunar-like. It's just crushed basalt. It's fairly pure material. We can use that as a field testing ground. We've done ground penetrating radar tests, for example, there where we buried rocks and ice blocks and things like that to see if we could find those. Another option that we have where we can do tests is the Quincy mine, which is again sort of a leftover from the mining days here. And it's publicly open in the sense that you can visit it. But there are some places in the mine that are not publicly accessible where you could actually do great lava tunnel testing like we were exploring over here. It's a pretty exciting underground lava alternative where you're not in national park, it's not nature, so you don't have to be very careful. You want to put a rock bolt in, no problem. It's also safely inspected because it's open to tourists. So it's a very safe place to work, well known. So here you can see some other things. So, you know, these thing is at a slope, so you could have a anchor vehicle and drive your vehicles down in it. And so there's some interesting things that we've been working on to explore underground facilities that way. Of course, when we talk about prototyping, we need to have facilities to do those kinds of things. And so we have mechanical, electrical build spaces. We have a lot of simulation capabilities as well. And in the meantime, we've built quite a few robots as well. So these are some older robots from 2021, but we have some more in the meantime. A little more details about some of these things. Lunar Simulant Sandbox. So in this simulant sandbox, it's not huge, but it is a nice size, 14 foot by 6 foot, and it's 1 foot deep. And so we can do excavation testing with our Lunabotics rovers, for example. In this case, we had built a slope simulating a crater slope where we would be driving down, and this vehicle can drive down a 45-degree slope over obstacles like this while deploying a cable behind it, which in this case would be power and communications. So you can see some more testing going on here. The other capability this sandbox has is we have a gravity offloading system in place so that we can simulate lunar gravity in the somewhat limited way of gravity offloading, but still it does a pretty good job with the traction side of things. Now, this, of course, is in an atmosphere. Still a relevant environment relating to the simulant. And so the traction and other kind of tests like obstacle stability and things like that are pretty interesting to do tests in 1G with. But nevertheless, it gives us a good idea of how the vehicles behave in lunar simulant. And this is a very important thing because, for example, the Lunabotics competition, one of the major challenges is for the vehicles not to get stuck. And so we can practice that in the simulant, and it helps a lot in the final performance of the vehicle. Now, like I said, we need simulant, of course, and we needed a lot of it, so about 30,000 to 35,000 kilograms. And so we made our own using the same ingredients as, for example, Exolit Lab, or I forget what it's renamed now, what it's called. But anyway, what they used to make. So the green spar, 90 and 250, and we had crushed basalt that we mixed in, and then the green dots here are the resulting particle size distribution, which is right in between the Apollo sample particle size distribution. And so we have a very nice particle size distribution. They are all crushed materials, so angular as well. It has a very good geotechnical properties. But the nice thing is we can make it for about $3 to $4 per kilogram. So that allows us to keep the cost manageable. Now, like I said, when we make icy regolith simulant, or we prepare things to go in a vacuum chamber, we need to be able to do that. And fortunately, it's cold in the winter usually, but we also like to do it in the summer. And so we have a big 40-foot freezer container in which we can do sample preparation. So we can see we have a big bin here that we can fill up, make layers, and then we can do our tests with ice mixed in, then do our tests we need to do. And then we can reset the bin as well, all in controlled conditions. We also have created a excavation test bed inside that freezer container. And so we are currently studying excavation forces under a variety of different materials. And so for Break the Ice Challenge, we have to use the controlled low strength material, which is a box shown here, which is essentially weak concrete. But we're also looking at cemented or particles ice mixed in with regolith, and we're looking at excavation forces of different systems under those conditions as well. And that includes different compaction levels, different percentages of ice, and things like that. However, now you have regolith mixed with ice, and that is not great when you put it in a vacuum chamber, so you have to make sure that it gets dried. And as you can see on the left bottom here, if the green spar, in this case 90, gets wet, it is like clay. It is very hard to work with. It's clumpy. And so that is not great lunar simulant. Not to mention it is wet. And so we have a 40-foot drying container here where we actually dry all our lunar simulant before we then either put it back in the freezer container for then controlled amount of ice mixed back in, or we prepare it to use in the vacuum chamber. So this is nicely dry, desiccated lunar simulant. And we do this at about 80 degrees Celsius, so it doesn't really change the mineralogy very much at that point. So talk a little bit more about prototyping and testing. So once you have an excavator, for example, it's great to have an excavator, but you need to attach it to something. But we don't really want to have a large vehicle to run around in the lab, drive around and stuff like that. So we have a robot arm that we can attach, for example, this excavator in, and then we can just do initial testing just to see how well it works. You see a first iteration on the left and then a sort of a second iteration on the right with some dust control mitigation issues and some other things that were addressed since then. Besides a large vacuum chamber, we also have a small vacuum chamber, and this one is particularly useful for small scale tests with either lunar regolith or under Martian conditions. It can only go to 10 to the negative torr, but it does have a little cryo shield in here where we can do liquid nitrogen cooling. And so we use this a lot for Mars testing. So you can see, for example, at the bottom right, an ice block that gets, in this case, we're testing melt probes there under Mars conditions, so about 7 torr, minus 80 degrees Celsius, and we're testing the efficiency of melt drilling, essentially. Now, the big vacuum chamber, like I was talking about earlier, this is a fairly unique facility that was custom designed and built for this purpose of simulating the lunar environment, but with large quantities of lunar dust in it. And so we can have this big box filled with lunar simulant that can be rolled into the vacuum chamber, and then we can take all the rails and all the moving parts out, and the box stays behind for testing. So it allows you to pre-install your test setup outside the vacuum chamber. You can prepare your test bed with ice if you want to, and then we can quickly roll it in the vacuum chamber in about 20 minutes. We can close the system up and then start the vacuum procedure. So 1 or 2 people can do this whole box at 1,500 kilograms and a test setup with no problem. It's very fast. We have 2 of these, so we can be testing one while we prepare the other one. When the one test is done, we can take it out and immediately put the other one in there and continue testing with another setup. I've got lots of feed-throughs and other things. You can read this at your leisure if you want to. Couple more highlights, right? So it's a reasonable size on the inside, 1.27 meters tall, 1.34 meters, 1.27 meters wide, 1.34 meters tall, and about 1.7 meters long. It can go to 10 to the negative 6 torr vacuum, that is with simulant inside of it. The thermal plate and shroud can be cooled with liquid nitrogen to minus 196, or with electrical heaters be heated up to 150 degrees Celsius. So it allows us to do thermal cycling as well. Got lots of feed-throughs and ports. The liquid nitrogen tank we have is about 3,000 gallons, which typically can last, let's say about a week if we do cold testing and need to keep it constantly cold. But that's, of course, dependent on the heat load inside. So some close-ups, we have roughing pump, turbo pump, and filter. We have the 2-circuit thermal shrouds, so we can control the bottom plate thermally differently, separately from the walls. And so that allows you to have still a cold bottom with icy regolith, for example, yet a hot shroud for simulating the lunar day, for example. We also can feed liquid nitrogen and other gases into the chamber for, let's say, localized additional cooling if needed. We have lots of power available in this space, 20 kilowatts of external power. We can feed into the chamber for specific tests, things like melting regolith or something like that. We have a programmable power supply and load. We do a lot of our electrical tests with that, lots of thermocouples and other data acquisition and control systems to go with this chamber. So it's a pretty cool facility to play with, which we do all the time. So some examples of that, right? So we've looked at vacuum regolith conveyance, and so how does conveyance differ in the vacuum from under atmospheric conditions? For example, regolith flow in hoppers. And so when you have a process, think molten regolith electrolysis or something, you don't want to just dump directly from your bulldozer or your excavator right into the reactor. So typically you deposit it in a hopper, and the hopper feeds it at a specific rate into your reactor. And so the question is, how well does that flow work? And if I do tests under atmospheric conditions, is that representative of the vacuum condition or not? And so we've done these tests in vacuum as well as in atmosphere to test the differences. I was talking about wear earlier, and so we've also designed and built and used a ASTM G65 wear testing machine that works in the vacuum chamber, where we can test various material coupons under a very defined load, with lunar regoliths being sort of dribbled by that for a given amount of time and pressure. And then you can study the wear characteristic of material under lunar conditions. The samples are cryogenically cooled, or I should say they can be cryogenically cooled. So they are at lunar temperatures. We have the lunar simulant being dribbled by, or whatever material you want, and then that simulates the wear over long periods of time. We also designed and built a vacuum-rated direct shear test. So this whole apparatus can go in a vacuum chamber. We can determine geotechnical properties of lunar simulant under vacuum conditions, and that includes these icy material as well. We've done an excavation in the vacuum chamber. We do a lot of thermal testing. Because we work with power systems as well, we have done 6,000 watt-hour battery tests in the vacuum chamber. We've done superconducting power transfer tests in the vacuum chamber as well. And then we look often also to the efficiency changes due to lunar simulant exposure as well. And other research that we have been working on are things like extracting water from Mars gypsum. It's an alternative source of water. It doesn't have to come necessarily from water ice, like glaciers. It could be bound in the mineral in the rock, such as in gypsum. Deploying cables for power down 45-degree slopes, very difficult terrain. measuring the geotechnical properties and volatile content down to 1 meter depth with a cone penetrometer. We've done field tests, as you can see, with these rovers that we've built, excavating cemented material, long distance driving on lunar simulant as well, talking about traction and how does a road hold up, for example. Those are the things that we've done. We, like I said, did vacuum excavation testing, and so this is, as far as I know, the first excavator that was ever used in a vacuum chamber. And so we've got a bunch of data on how the excavation occurs and how it's different in atmosphere versus vacuum. Some more details about some of these projects that we've been working on. One that we are very interested in is lunar excavation testing. And so we work with simulant, but also with cemented ice, or the alternative, like the controlled low strength material, the weak concrete, or for example, gypsum excavation as well. And so one of the things that we're very interested in is using bucket ladders. They have small scoops, which means small excavation forces, and there are a lot of them. And so you have a high production excavation capacity, yet you have small excavation forces because of reduced gravity. Both of those are a good thing. And so we have our own bucket ladder here, and we have one from an old SBIR project that we want to mount on this vehicle here, and we want to go actually dig a 1 meter deep trench and see how our bucket ladders hold up. Right, we've tested them in the vacuum, and now we want to test them in the field as well. And then the excavation test bed in the freezer container, we really want to explore the icy regolith, whether that's cemented or not, excavation, and how the excavation systems hold up with that cold cemented material as well. So this measures the excavation forces in the 3 directions while we are excavating the various materials. Then water mining and extraction on Mars. I already sort of mentioned the gypsum here, right? So we've done work on, disintegrating the gypsum with, in this case, a water jet, sucking up the slurry, the mix of water and gypsum powder, and then putting that in a reactor to then heat up and extract the water from the mineral as well as the liquid water from the water jets, and then recover that all. So that whole process we have tested and brought to about TRL4. But also we've looked at extracting water from buried glaciers together with Honeybee Robotics. We were looking at the melt efficiency and drill efficiency of melt probes in under Mars conditions. And so you can see some of that work on the left. Then the big project here, which is our Luster grant, which is a percussive hot cone penetrometer and ground penetrating radar for the purpose of geotechnical and volatile quantification and mapping, right? And so this is intended to determine how hard it is to excavate the lunar material and map and detect how many volatiles and which kind of volatiles are embedded in the regolith. And so you can see that there's different aspects to this. We have the geotechnical aspect, and so we measure the forces on this cone while it gets percussed into the ground. And you can sort of see the data example here where you measure the resistance if you go down, and then that translates into regolith geotechnical properties. At the same time, we stop every 10 centimeters, and then we heat up this cone over here, and we collect thermal profiles. From those thermal profiles, we can then infer whether or not there is a volatile mixed in, or whether it's dry or not. And you need to combine that with geotechnical information, because you need to know the relative density of the material, because that greatly affects the thermal properties of the material. And so the combination of the thermal data and the geotechnical data is what allows you to uniquely identify whether or not there are volatiles in the regolith, or if it is just, let's say, less compact material. Then the ground penetrating radar maps in between those points where you applied the cone penetrometer to see whether or not you have nice uniform layers or if you just happen to hit the dry spot, if you will, or you got lucky and you hit the one ice cube that was buried there, but there is no water in the surrounding area. And so the GPR really allows you to sort of map in between and interpolate between the test points of the cone penetrometer. Now, ice is what we were talking about, but there are many other volatiles in the lunar simulant as well. And so the tricky part is that they are mixed, and there's no necessarily unique challenge or unique signal of which volatile is in there. And so one of the things we are working on right now is to create a thermal profile database in a way of how other volatiles mixed with regolith heat up, and what is the thermal properties of that material. And so we've created a test setup that allows us to cryogenically freeze and cryogenically test other volatiles that are mixed with regolith in a vacuum vessel, and then create those similar thermal profiles as you see here for a different mix of different volatiles, like hydrogen sulfide. We have like carbon dioxide, and there's many others that we can do. Now, we want to, of course, not endanger the people that do this work, and so we have to be very careful and safe with all these kinds of volatiles, some of which are very dangerous, like the mercury. Hydrogen sulfide is also very dangerous, so we need proper PPE. This is all done in a big fume hood and things like that. The full system was designed to do both the geotechnical measurements and the thermal system. And so just this past couple of weeks, we've done our final tests for this project. And so as you can see here, we have this big bin created with different layers in it. So it's icy regolith and things like that. This example was 0, so dry regolith at the bottom, 3% ice in sort of the center layer, and then 0 dry percent again at the top. And then we did a big thermal test in the center, right? So 10 centimeters, do a thermal test, do another 10 centimeters, do a thermal test, and then a lot more geotechnical tests around that, because the thermal tests take a long time to do. And so overnight, it takes to do all of these tests in one time. Then we did a large field test, as the full system is not just in the box, but also drive around with the GPR. And so we did that at the Keweenaw Research Center. We built a relatively large trench, 7 meters long, 1.2 meters high, and 1.5 meters wide. And we built 2 different zones, right? One with 0, 6, and 0.8% water, or ice in this case, and then the other with 9% at the bottom, 3% ice in the center, and then dry regolith on the top. And that's what we aimed to make, and then here is what we actually measured and actually created. So it was pretty close, because at the time it was snowing, as you can see here, and it's hard to keep everything totally dry when there's literally snowing on you all the time. We mixed the regolith with the ice. In this case, these were fresh fallen snowflakes, which are very fine, which is really nice. And then we filled the test bed. As you can see here, we have one zone being filled, right? Just mixed in a cement truck. And then the simulant gets deposited in layers, in different mixes with different water contents, and then compacted. We were experimenting with different compaction methods, and that, I can tell you, that's very challenging actually to do. But anyway, so we succeeded in making all the layers that we wanted, and then we were ready to do our testing. Now, unfortunately, the winter this year was the hottest one on record, and we had only 4 days where it was cold enough here to do this test in a row. So we made the box on Friday with all the layers, and then we had 31 hours nonstop to do this test before the temperature was above freezing again, and our ice would start to melt. So 31 hours nonstop, we worked through the night. We had our ground penetrating radar test set up here where we drove over the trench. And then we had our cone penetrometer also mounted on here. And so we then did our cone penetrometer and thermal testing as well. And then, like I said, we worked 31 hours nonstop to get all the test data that we could before it got too warm again. And then you can see sunrise here. We survived the night. It's a little different than on the moon, but we did survive the night. after 31 hours of testing, and then we got it done right before things started to be too warm. So just an example of the data, we're still processing the 2 gigabytes of data. We haven't finished that yet, but you can see some GPR data. We see the left side and the right side. There's clear layer differences, which is good. And then this artifact is a wooden separation thing, so it's not real lunar dust or anything. It's just wood, but nevertheless, you can pick up that there's something there. Then we have some examples just here of our test data from our thermal data here, different locations, different depths, and different ice contents. And so again, we're still processing all this data to see how it all looks. But the data looks good, the data looks clean, and so we are very excited to get all that data and compile the results. All right, switching to another project, the autonomous landing pad construction, where Michigan Tech is a subcontract to the Colorado School of Mines, who is in charge of the Aspect rover, and we are focusing on the compaction side of the landing pad construction side. And so we have designed and built a test setup here that allows us to compact lunar regolith down to 30 centimeters depth in one go. And so depending on the starting condition of the regolith, we are able to get very close, and these are just preliminary results, to 90% relative density, which is the desired target. And so with some tweaking and further testing, we are confident we can achieve 90% relative density with this compaction method. A little bit more about what's on the moon, the competition. And so the idea here is to provide power from a power plant on a crater rim somewhere down into the permanently shaded region where you would be extracting and mining ice. And so our idea was to use a superconducting cable because in the permanently shaded crater, it is cold enough to go below the critical temperature. And so we can use a superconducting cable to transfer power over kilometers of distance without any losses. And that means you can use a very light cable because there's no resistance in it. It also means there's no heat generation in the cable because of that. And so a very thin cable is sufficient for that purpose. And so this is part of what T-Rex was doing, but then we used that design in the Watts on the Moon challenge. And that was for power transfer to a plant in this case. So we got some pretty good watts per kilogram transferred, right? So if you could only use superconducting tether, you can see the efficiency of watts per kilogram transferred to be really high compared to, let's say, only a conventional tether made out of aluminum. Right? So that's a big difference in efficiency of power transfer. We did a bunch of trade studies, of course. So we looked at what conductor material would be the best, depending on temperature and what dimensions that the cable needed to have, et cetera, et cetera. And all of these trade studies led to a particular design, including power conversion on what we call the upstream side, which is the power source, then the power transfer down to where you need it, and then the downstream side, which is where that power needs to be stored in in our case, a battery, about 6,000 watt-hour battery, and then it provides power to a NASA load as specified in this graph here. So this is all part of the competition. So our solution includes that superconducting cable for power transfer, but also all the electronics and the battery storage as well. And so we've been testing all of these different components. You can see the power transfer testing, the converting power converter, the power transfer system here, superconducting, as well as the battery tests in the vacuum chamber. So this is a 6,600 watt-hour battery in our vacuum chamber being tested for discharge and charge cycles under vacuum conditions as well. And so this is going to be tested in NASA Glenn's vacuum facility this summer. During the final round, and that's where the thermal aspect really becomes very important as well, because it will go in a liquid nitrogen cooled vacuum chamber, and so our system needs to be able to properly operate under those conditions. And so we've been testing that power, but also especially the thermal design of this system. I'm not going to tell you all the secrets of that today, but you'll have to wait until after the competition to learn more about that part. Then the Break the Ice Challenge, which is the last part I wanted to cover here. And so this is our phase 2, level 2 prototype called Primrose, which did the durability demonstration test where we are targeting 800 kilogram excavation per day and driving 500 meters between excavation site and deposition site, and do that for 15 days nonstop. Right? This is a full-scale, full-size system, which, if it functions with 800 kilograms a day, is enough to actually refuel a rocket on the lunar surface. And so this is essentially a full-scale demonstration of ice mining system on the moon. Now, the durability demonstration testing required a proving ground to be built so we could actually do that testing. And so here you can see a picture of the tent city that we built with the excavation tent, the driving tent, the lunar simulant driving tent you can see in the top right here, and then our deposition tent on the right. And so we had deposited 16,000 kilograms of simulant in here that we needed to drive on, which was our version of the lunar surface, basically. And as far as I know, we're the only ones that drove on lunar simulant for the entire duration here. And then, of course, the excavation area was specified by NASA to contain the controlled low-strength material, so very weak concrete, essentially, but cemented material. And this whole area here was staffed 24/7 for 15 days by the students that are part of the team. So here you can see some more details of that. We had a large 50-foot long tent for the excavation area, a 40-foot long tent for the drive area, and then a 20-foot tent here for the deposition. And so inside we had that big box where we needed to do the excavation, and then our drive area where we needed to drive that 500 meters. Now, obviously, this is not 500 meters, so we needed to drive either in circles or, in our case, we decided to go back and forth like it was on a regular road, basically. And then we had our deposition area over here. So we ended up excavating quite a bit, but not quite the desired amount because we built and designed the system in a relatively short amount of time with students. And so there were quite a few things we discovered during testing that needed to be improved. But again, we had to mix the regolith, we had to prepare the drive area, we had to, of course, prepare and pour the concrete 28 days in advance, so it had time to harden. And then the tests would start for 15 days, 24/7 operations. And Primrose was all ready, and we were ready to go. So we started excavating and excavating some more and driving back and forth. And as you can see, we drove many, many times over this patch of lunar regolith. As a matter of fact, we drove 30 kilometers on this patch of lunar regolith. And so that's about 3,000 times roughly on that same stretch of lunar regolith. And that is a lot of driving on, let's say, the lunar surface. And so we learned a lot about deterioration of a road. And if you dig yourself in a hole, how can you then fix that hole by driving close to it so the hole kind of collapses in on itself, and you can compact it again by carefully half driving on it and things like that. So we had a lot of lessons learned about driving on the same patch of lunar simulant, basically. Anyway, in the end, we excavated about 3,000 kilograms, which is about a quarter of what we needed to. But a lot of that is adjusted now by design improvements for the final round, which is coming up in June. And so we have some upgrades to the vehicle, as kind of shown here. And so the level 3 testing that we're going to be doing in June will entail 2 parts: a 1-hour transportation test system, and so you can see the loop that we have to drive over here, and then 1-hour excavation with gravity offloading. And so we have to excavate for 1 hour and fill up our entire system, essentially. And so we have an improved excavation and material handling system, improved storage and release system, and we have a much more robust driving system so we don't get stuck like we did in the lunar simulant. And here you can see the updated chassis that's ready to go. The control system is now all implemented, and we're in the process of testing our system right now. And so as a final slide here, what are the next steps, our future ambitions? Well, NASA has ISRU missions planned, and We have lots of technology development that's related to the NASA mission objectives and can directly fulfill some of them. And we are in training a lot of students with space hardware experience that are quite in demand with lots of our partner companies to hire them afterwards, which of course is the main product in the end of a university, which is educated students. But yeah, our goal is to be part of a lunar surface technology mission to demonstrate as well as then help companies really use that technology in the long run. So we'll partner with you, and hopefully you can partner with us and we can make this happen. So with that, if there's any time for questions, I'd like to open it up for that. Thank you very much.
Great talk, Paul. Really cool, really cool work. I am looking at the Q&A and I don't see anything, so I am going to jump in with a question. Um, did two parts to this. For your Break the Ice Lunar Challenge, when you were driving back and forth over
Mhm.
that same area, which 3 kilometers, that's a lot, or 30 kilometers, that's a lot. Really well done. Did you notice, would you slip or have wheel slip every time you were going back and forth across it? Or did that frequency increase with time? How did performance go as you drove more across it?
That's a great question. So the answer is it depends. um, there are a couple of things we noticed. One, um, there is air trapped in the regolith, and it actually changes the
Mhm.
behavior quite a lot. And so when it
Yes.
is loose and fluffy, and you notice you've worked in regolith boxes as well, so it almost becomes liquid when you have a big hole that then collapses in and stuff like that. And so you have to be very careful. It's almost like quicksand in a way,
Mhm.
um, except that you will just sink to the bottom and not float. So it is pretty tricky that sense. Um, One of the challenges that we noticed was with our wheel design. You can sort of see the V shape here of the grousers, right? And
Mhm.
so depending on the direction that we drove, the V shape essentially would trap air in that V shape when it was going down in the regolith, and then there would be a big poof of regolith coming out when that
Okay.
air would be pushed out. And so that obviously doesn't happen in a vacuum, right? And so the behavior is actually fairly different in that sense. Um, Now, we did notice that the regolith tended to sort of be pushed away and sort of spread out, if you will. And you
Yeah.
definitely created the ruts from driving in the same place because you can't constantly move the regolith a little bit the way it was. We weren't slipping a whole lot as far as the rim itself, but based on our wheel design, you could definitely move the regolith all the time. It was constantly being pushed a little bit in one way because of our grouser design. And it tended to pile up sort of at the beginning and the end of the track in a way, which
Yeah.
was quite interesting to sort of see. We're slowly plowing it one way and then the other. And so you can kind of see if you compare the left side of the track here to the right side, that the right side is definitely lower. Right? And so we've
Mhm.
definitely sort of plowed, slowly pushed the material away. So that's part of what we're noticing. And it wasn't so much slipping as well as just because of our particular wheel design that moved that stuff along. But a bigger issue was that we were not controlling the load distribution on the wheels. That's
Mhm.
something that we wanted to do, but we didn't have time to fully implement. And when our vehicle was fully loaded, so the vehicle is about 330 kilograms and it can transfer about 270 kilograms of material. But if it was fully loaded, when you go on just uneven terrain, the load gets unevenly distributed on the wheels, and that meant that the wheel that got all the load actually dug itself in,
Yeah.
right? And by doing so, now it was redistributing the load to the other wheels. And when they finally got traction again, now the one wheel was stuck in a hole. And that was challenging. And now our wheels can go up and down. We have vertical suspension on each wheel individually. And so we could move the wheels up and down and get out of that. Um, But that is actually one of the major control issues of these heavy vehicles that you have to be aware of, is the continuous management of the load distribution along the wheels so that you don't have one wheel that digs itself in and then you don't have enough traction with the other wheels to pull it out if you're not careful. And so that was one of the major things that we noticed when driving on the lunar simulant here.
Interesting. Thank you. Great explanation. Now, so sorry everybody to take for that from my question. There are several in the Q&A now, and we'll get to a few of these here. Jason Matthews asked, "What are your thoughts on site planning? Which infrastructure items should be prioritized in order to reach long-term goal of large-scale autonomous resource utilization projects?"
That's a great question. So I, one of the challenges I think that has not really been solved in my mind is, Phil Metzger has been working on this a lot, is the damage and potential effect of plume effects of landers, and then of course subsequent launches off the lunar surface. And so if we're going to build permanent infrastructure, um, I think if we go to the same place all the time, one of the first things we'll have to build is something that prevents damage to your other emplaced assets when you launch or land your vehicles close to them. And when I say close, it means within distance of either driving or walking of the astronauts, depending on the safety requirements that you have with that. And so landing pad to me is one of the first things that need to be built. And then the second part is really, I think, some form of road. And what form that takes exactly is to be determined. But one of the biggest challenges in my mind is dust contamination. And so when you are going exploring, you're always driving on new terrain. You always got to drive in new regolith. And so, of course, you want to not contaminate yourself. But when you have a lunar base, one of the big challenges is to not get the dust inside and contaminate all the other things that are there for permanently. And so having a surface finish, something that prevents the regolith from being spread and kicked up, and go to places where you're really trying to keep it away, I think is going to be very, very crucial. Um, so we've been working on some technologies to that effect. I can't go into all the details, but one of the interesting findings, I think, is that I think zoning is going to be really important to limit the dust spread to places where you do not want it. And what I mean with that is that if you have, for example, a mining rover, all right, that drives on just dirt roads all the time, it shouldn't be coming to an area where you are trying to really keep things clean, right? And so maybe you need sort of a special vehicle that only drives on the clean areas. And so think of a surface finish that's different qualities at different places, depending on how clean you want to keep the place. I don't know if that answers your question, but those to me are kind of two of the key items that we're going to have to start with.
Perfect. Um, Great explanations. And next question is from Gustavo Yamanka Lino. "Hello, could you please detail more about the concept for water production on Mars from gypsum?"
Yes, I can. Let me see if I can go back to that slide. But the gypsum is an interesting material. You may know that we make drywall out of that here on Earth. But the idea with the gypsum is that it has 20% water by weight in it. And that water is not liquid water like groundwater. It is actually physically bound in the mineral structure. And so it is part of the rock, right? So like you create a cast here on Earth, right? You start with plaster, you mix water in it, and it hardens back into gypsum rock, in this case around your leg or whatever, if, to keep it in place. But the rock in nature has 20% water in it, assuming it's fully hydrated, which does occur and has been detected on Mars too. And so the nice thing about the gypsum is that that water comes off at a relatively low temperature, meaning between 150 and 210 degrees Celsius. And that is much lower than some other minerals, for clays, for example, that have more water in it, but then you need to go to 400 or even 700 degrees Celsius to get that water and break that bond. So gypsum is very nice in that sense. It's a very soft rock. It's about 30 megapascal maximum compressive strength, and it has low temperature to drive off the water. And so it's a very good candidate to extract water on Mars from a rock if for whatever reason we can't get to the ice, right? Maybe it's too hard to drill down to or something, although honeybee has kind of, I think, solved that. But there might be like planetary protection reasons we can't use that ice or liquid water. And in that case, being able to extract water from rock as an alternative is a viable means to do so. And so this technology here, which disintegrates the rock using a water jet, makes a slurry and kind of powder, but then mixed with water, and essentially you create a shop vac that sucks up that slurry, and then that slurry gets deposited in this, and essentially it's a pressure cooker, right, where you heat it up and you catch the water vapor coming off, you cool it down and distill it in a way, and then the dry powder gets discarded on the other end. Could be a future construction source, perhaps, right? If you want to make drywall on Mars in the future, and if we do have access to those glaciers, you could mix water back into it and create drywall if you wanted to do that. But yeah, that's kind of what this project was all about. Did that answer your question?
We'll assume yes for now.
Okay.
Really cool stuff. Last question before we end here, since we are yes, that did answer their question.
Awesome.
Um, Theodore Miller asks, what were your compressive strength results for the CLSM, and what mix did you use, i.e., ratio of cement, sand, and other?
So our resulting compressive strength test was about 1.75. It was actually right in the middle of the target zone, because the target that NASA specified is was 1.5 to 2 megapascals of compressive strength. So we were at 1.75. Now, unfortunately, I do not remember what the exact mixture was. I can look it up, but I don't know off the top of my head. I do know that we had to make about 10 test batches before we got the mixture just right. And part of that was actually because the cement plant where you would order the cement can't do small batches very precisely. 100 liters more or less water is sort of standard, and so it's pretty tricky to get it just right. And so for small batches, we were actually not able to test it, so we have to hand mix it and do that, and then we can order the right bigger batch from the plant, and so then a little bit more or less didn't really affect the results so much. And so we ended up right in the middle of where we wanted to be, and so that was good for us. So about 1.75 megapascal.
Cool. Trial and error. Perfect. And with that, since we are a bit over time, I'll call it here. Paul, thank you so much for lending your time and all the great information. It was a really cool and informative talk. I appreciated it. I'm sure everyone else does too. For now, we'll sign off. And until next month, everybody, keep an eye out for next month's announcement.
Thanks for having me, Jared.
Bye, Paul. Bye, everyone.
Bye, everyone.